Last class we were doing this whole stuff on recognizable, and I found a few more slides on the topic, so I thought I'd just do them here. So what do we know? The recognizable languages are the ones that for which there's a Turing machine that distinguishes between yes and no answers by halting and saying yes on the ones that are yes instances, and running forever, or maybe halting and saying no on the ones that are no instances. And I think I sketched briefly the algorithm for solving the halting problem, which is simply run m on it, and if it halts, then halt. But what I haven't done yet, this was part of our list of problems that, given a Turing machine, does there exist an input for which it halts? You might remember that we proved it was equivalent to the halting problem. At least we said it was equivalent to the halting problem. We didn't actually prove anything about it. We said it was equivalent to the halting problem. And we said that the for all value, for all inputs m halts, that it was harder than halting and not halting. All right? So I just thought I found these slides at the end there, and I rearranged all the slides, so these got skipped. Here's a little bit of code which is going to prove that this problem is recognizable. And there you have it. So what is it supposed to do? It takes as input a Turing machine, and it tells you whether there exists an input on which that Turing machine halts. And the obvious thing to do is to loop over every input and then run m on I, right? And if it halts, then stop and accepts. We're trying to find an input on which it halts, so we just loop over the inputs and check. Does this look like a good algorithm?
How do you iterate over I?
Well, that's not a problem. I is just thought of as a binary string, and there are a million ways of iterating over inputs. We can do that without too much stress. What? What's bad? Sorry, what? You are so good. He always comes up with good things. I like it when he talks. All right. So if on some I, in fact, on the first I it does. If on the first I it halts, then we accept. But if on the first I it doesn't halt, then we never get to the second I. Right? So either way, actually, we never get to the second I. So anybody have a solution to this?
We get into an oracle.
We don't have an oracle. We want to do it all by ourselves. We did something like this similar. So what do you think we want to do? Yes?
Maybe feed it into another Turing machine, and then if this one halts, then it moves on to the second input.
But if it doesn't halt, what do you do? Isn't that what we're doing now?
Okay.
Yeah.
I'm in parallel.
Run all. Yeah. So the one thought is to run all inputs in parallel,
If one stops.
right? But what's the problem with running all inputs in parallel?
Infinite time to power.
Right. So you never get to the same time step. Yes.
If it's a machine that runs P hard.
P hard. What? P hard. P hard is probably a problem that's undecidable, so we don't have a machine that runs P hard. Now, we do have the idea, this idea of running them in parallel is the idea of run m on a particular input for some t time steps, right? So we want to think about the order of, right, we have some input and we have some time step, and we run m on I for for t time steps.
Then loop for T plus one.
Right?
Nothing holds, then loop for T plus one, then T plus two.
Yeah, so if we loop first over the t's, we'll never get to the second I. If we loop over the i's, we'll never get to the second t. Right? So you've seen solutions to this before.
So run all the inputs for one time step. If nothing holds, then two time step.
If you run all the inputs for one time step, there are an infinite number of them. You'll never get to the second time step. So let me ask you a completely different... Yeah, you have a suggestion?
Run like the inputs for like some polynomial time, and you decide what that length of time is.
Well, that's fairly what we're doing here. We're deciding what length of time to run it.
We define t on I,
Define...
t over I. T is a function of the input and
T over I.
no, I mean t is defined by I.
Yeah, so that's sort of saying maybe t is a polynomial in the length of I. But so let me ask you, let's do a review class instead, since you guys are having a hard time. Fractions. Are the fractions countable?
Yes.
Why are the fractions countable? Right?
Actually, 1 plus 12.
The diagonal thing. What was the diagonal thing? We have here some I over some j, and
That's real.
here's I. No, if it's a fraction, I over j is a fraction. J, and so here's 3/4, right? And we sort of do a diagonal, right? In fact, we said in general, suppose we had a tuple I, j, k, right? We wanted to loop over all of them. It's good that we're doing this because I was thinking about putting this on the exam, and then I was thinking, now, are people going to remember this? But here, this is proof that no one here was really going to get it. So, anybody remember how you could loop over all these tuples and get to each of them?
Make the sum.
The sum, right?
Could you explain what is the sum?
Loop over the sum, and here I equals 1 to sum, 0 to sum, j equals 0 to sum, minus I, j equals sum, minus I minus j. So this is doing diagonals. So you first say, you loop over, in this sum, this is a loop 0 to infinity. All right? 0 to infinity. And once we know the sum, then we know that I, assuming I, j, and k are positive, we know that I is between 0 and sum, so we can loop between 0 and sum. And once we know sum and I, we know that j is between 0 and sum minus I, right? And then once we know sum I and j, we know what k is, right? And then we can handle ijk, right? Now, what this ordering is right? It's a list. We're listing them all. We're going to talk in a minute about enumerating. We're enumerating them all, and because it's a computer doing it. The computer's enumerating them. And what's special about this ordering? Do we ever output every tuple?
No, but sometimes that if you give the time, there will be. If you give the answer, there will be a time where that answer will be printed out.
Exactly. So there's an infinite number of tuples. So at no point will this, no finite point in time will the algorithm have outputted all of them, right? But as said here, if I tell you a particular ijk, 3, 8, 17, you're going to be assured that it will someday get printed. Why? Because you figure out what the sum is, and eventually you'll get to that sum. And each of these lists terminates, right? So the sum will eventually get to the sum, and then I will eventually get to 3, and J will eventually get to 8, which will make K 17. Does that make sense? So let's go back to our question here. We want to schedule. We have some input I and some time step t, and we're going to run m on I for t time steps. How do we schedule these i's and t's?
We do something.
We do a something. Exactly. So here what I'm saying is we just enumerate overall I and t so that eventually you get to each I and t. Each I t pair, eventually you get to it. And what you do is m, if m halts on I after t's time steps, then we halt and accept. Yes?
Can you explain again what we're doing and what's the point of what we're doing?
What are we doing and what is the point? Those are very deep questions. All right? So, there are various letters to what we're doing and why we're doing it. So, what we're doing is we're proving that this is the problem, given an input m, does there exist an input on which m halts on it? Right? That's a computational problem. And that problem, we've already proved, is at least as hard as the halting problem. So it lives from here upward. Ooh. Feedback. Maybe the mic is up here. The speaker is up here somewhere. All right. So anyway, we did prove that this problem, if you could solve the halting problem, you could solve this problem, right? So what we proved already is if you could solve this problem, then you could solve the halting problem, right? So this proves that this problem is harder than the halting problem. But now we're showing that actually it's still recognizable. There still is a Turing machine that that can recognize this language. And what that means is given an M, it can recognize whether it's a yes or a no. And the way it recognizes it is it halts if it's a yes and it runs forever if it's a no. All right? So that's what we're doing. And how we're going to do that is we're going to write an algorithm that if M halts on some input, then this algorithm is going to halt. And how does it do it? Well, we enumerate overall I's and T's, right? And we run M on I for T time steps. So suppose there existed an input on which M halts on I, right? So do I have this? Yeah, here we go. Suppose there existed an input which halts on I after some T time steps, right? If it halts on I, it halts after some time steps. So the tuple IT will eventually be reached in this ordering, right? And so then our algorithm here will halt, right? But if M runs forever on every input, which is the opposite case, well then this algorithm is going to run forever, right? So everybody see how this recognizes this problem. And then the question is, right, so that puts this up here. And then what one might ask, how does one order those I's and T's? And we do that diagonal thing. And here we go. I guess I is the sum. Maybe I should change this so it says sum. It would make more sense. And, right? Same idea. Everybody good with that? Yes?
In that loop that we had before we came up with this T time step idea, wasn't that still recognizable? Because at one point it might not halt, but it also might run forever. Isn't that still considered that it's recognizable? Because there's still...
So this algorithm?
No, the first one, before this
Oh, the first one.
And was this a good algorithm?
No, the first one's a bad algorithm because if M halts on the first input, then it will halt on the first input.
I got that, but is that still considered recognizable? Because if the first input is, you know,
Yeah, but it could be it's a yes instance because it halts on the second input,
right?
and this thing is going to run forever,
Oh, okay.
right? You want to make it sure that it halts in every yes instance, not just trivial ones. Are everybody good with that? And that brings us nicely to this next topic, which is the concept of a computational problem being enumerable. And I know what we need is yet another definition, but we're only going to spend 2 slides on it. All right, so though I think it's an important one, and I think there might be a question on the assignment about it. Anyway, we say a computational problem is enumerable if there exists a Turing machine that might run forever. And what it does as it runs forever is it keeps spewing out yes instances. And it never spews out no instances. And each yes instance will eventually be outputted. Right? So that's called enumerating the yes instances. Right? Yes.
Can you say that again?
Yes.
All instances will never be outputted, just the yes ones?
Yeah. So the definite. Remember, we've already had a definition of a set being countable, right? A set is countable if you can list the items in it, right? 1, 2, 3, 4, 5, 6. You list them, right? So here the question is similar to countable. We say the set is enumerable if they can be listed, just like in countable. But the difference is here the listing is being done by a Turing machine. It's computably listable, right? So what this Turing machine does is it prints out some yes instance, and it prints out another one, and another one, and another one. And it never prints out no instances. And given it, of course, does it ever print out all the yes instances? No, because there are an infinite number of them. But it eventually, given any particular yes instance, it eventually outputs it. All right? So you might note, I put it up here in the same color right next to each other. And the reason I did that is because we're going to prove that if it's recognizable, it's enumerable. And if it's enumerable, it's recognizable. All right? So let's first, you want to think about how do you prove if it's recognizable, how to enumerate all the yes instances. All right? So we have, imagine what we have is a Turing machine that if you give it in an instance, it will halt and say yes on the yes instances. Right? So what we want is to print out every yes instance. Never halt. We're going to never halt, but we're going to print out every yes instance is eventually going to be printed out. Right? So same as here. Very good. That is the killer answer. Same as here. In fact, that's why we're doing them right next to each other. What do? It's the same algorithm. Given an accept algorithm, we enumerate them. How? We loop over all I and t in a diagonal sort of way. And if m halts on I after t time steps, then we output I. Now, of course, this is going to output a particular yes instance many times, but that doesn't matter. We didn't say that was a problem. If you wanted to, you could check to see whether you've outputted it before and not output it again. But you'll see here that if I is a yes instance, then M except halts after some number of time steps. So eventually the tuple IT will get to it in our diagonal ordering, right? And this program will output I. Right? Does that make sense? And similarly, it never outputs something that's a no instance. Right? Everybody good? Wait. Yes.
Can you explain again the importance of why you do the T time steps again?
It goes back to if we ran M except on a particular I forever, we would never get to the next I. Right? If we fix I and loop over all and have T be arbitrarily big, then we would never get to the next I.
But what happens if you don't have T at all? You can't simply just loop over every input.
No, that was the problem, because if you looped over the inputs, we would never get to if the first input didn't halt, you'll never get to the second input. So you hit the first input, you run M on the first input. On the first input, it runs forever. So what does this do? It runs forever and it never gets to the second input.
So those T time steps are there so that way even if an input is really, 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 really big and the machine will halt, it's there so that way it moves on to the next.
Yeah. Yeah, it's a way of running the inputs sort of in parallel, but not completely in parallel. It's sort of diagonal in parallel. Yes?
You're shrinking the size of the problem because there are some input that will accept in less than T time steps. So you're shrinking so you can move on to the next one.
Yeah, if you wanted to keep track of these things, if you wanted to say, I've already run this, I've already accepted this, so you don't have to run it again. There certainly are ways to make this more efficient, but we're not looking for efficiency here. All right, so let's go the other way. Suppose I have a Turing machine that enumerates all the yes instances, right? And now up here, we want to come up with, we want a Turing machine that takes as input a particular input and wants to know if it's a yes instance. How do we do that?
You could read the next symbol.
Which symbol?
On the Turing machine, on the table. On the table, I'm sorry.
I don't know.
You can check the list, the enumerated list, if the answer is there.
Exactly. You got a list here. You just check the list, right? So you run this Turing machine here, right? Given an input I, you run the enumerating program, and if I ever gets outputted, then halt and accept, right? Now, what does this program do? You'll note. Do I talk about it? If I is a yes instance, then eventually the enumerate program will get to it and will halt, right? If I is a no instance, you'll never get to it and you'll run forever.
Of I, that should be outputted, right?
What?
You say if I gets output.
Yeah, if I gets outputted by enumerate, right? We're running enumerate and we're watching what gets outputted, right? And maybe this should be indented further or something. Everybody good with that? So that shows that those two are equivalent. Any questions? Yes?
Could you explain again how looping over tuple works? I still don't understand how you use the concept of sum to eventually get to I, J.
Well, I don't know what the sum here is, 25, 28 or something. So these, for each sum, these terminate. right? Because this is a finite list. So you're going to get to each value of sum. So you eventually get to sum equals 28. And when you get to 28, then I loops from 0 to 28, so it gets to 3. And when we have 28 and 3, j loops to 0 to 25, and it will get to 8.
How does it get to 3 and 5?
Well, we have a loop, loop, loop. Oh, sorry. Three loops. Right? So this loops until we get 28. And this loops until we get 3. And then this loops until we get 8. And then this equals 17. And we print out our value.
So are you saying that this essentially just goes over every combination of a tuple?
Yes. That's our goal. That's what we're going for. Is we're going over every combination of tuples. And what does it look like? Is you have a three-dimensional thing, and then you have the sum specifies a particular plane coming out here, right?
That has properties I, J, and K.
Every I, J, and K on this. This is I and J and K. This plane has a fixed sum, and then you knew that area of that is a triangle that has a fixed area, and so you enumerate over that triangle. And then you go to the next triangle. Well, this here happens to form a triangle, this plane. Well, because it has 3 corners. Yes? What enumerate does is it eventually prints out every yes instance. Every yes instance eventually gets printed out. So what mexcept does is it runs we're trying to prove that if we had enumerate, then we could have an accept thing program, right? And what is the accept program supposed to do? Is when I is a yes instance, it looks to see if I is on the list, and it will be, so it halts and accepts. And when I is a no instance, it won't be on the list, so it's going to run forever. And so that's where we have this definition up here, that if a problem is recognizable, there's a Turing machine that always halts and accepts on the yes instances. Any other questions? Is everybody enthusiastic? Yes?
I was just confused when you say if the Turing machine keeps running, it doesn't output anything much, but then you're saying now that it outputs yes, yes, yes.
Oh, the enumerating program?
Right.
It keeps outputting yes instances. Right? This Turing machine, enumerate, what it does is has no input, it runs forever, and what it does is it outputs yes instances. Right? And the point of it is, right, is that each yes instance will eventually get printed.
But then it's going to halt.
No, because there's an infinite number of yes instances. It's never going to halt.
So how is it recognizable if recognizable problems halt and accept on yes instances? Again, can you quickly go on over that? Like recognizable problems on yes instances halt and accept. Right?
Yes, that's the definition.
Right. So you have put recognizable and enumerable at the same level.
Right.
And you also proved it, right?
Yes.
The other way proved. Could you go over it again?
Yeah, well, we did both directions, right? This direction, right? We said how do you enumerate, right? We did this IT thing, right? Which came up with enumerating. All right, so what we're going to do now